Ready?
Yes.
Okay, so it's a pleasure to welcome Mina Karzand to our CCSP seminar series. In fact, she's going to close out our seminar series for this semester and we'll be back in force next semester. Mina received her PhD at MIT in EECS, and then she was a postdoctoral associate there, after which she has been a postdoctoral associate at the Wisconsin Institute of Discovery at the University of Wisconsin in Madison. And currently she's a research assistant professor at the Toyota Technological Institute in Chicago. And very soon she'll join the University of California, Davis as an assistant professor in the Department of Statistics. Congratulations. Mina Karzand's research interests are in machine learning, information theory and statistics, applied probability theory, aspects of theoretical computer science, and she's worked on inference in icing models, active learning, collaborative filtering. And today she's going to speak on a problem in online learning, and that work looks at collaborative filtering. So Mina, it's all yours.
Thank you. Yeah, thank you. So this is a talk about online collaborative filtering. And this is basically work on like two papers that one of them got accepted to IT transactions and the other one is being prepared right now. So I'm gonna try to not to go through too much details of the proofs to make it like bearable, but still like give enough intuition to understand what are the interesting points of this work. And if you have any questions, please don't hesitate to interrupt. So first, I'm going to just talk about the system requirements. So at the core, this is about system design. I'm going to tell you about the system requirements for the online recommendation systems that I have in mind, and then introduce the measure of performance, how I assess the system that I will design, and introduce the model for the preference model of underlying this system design. And then I will introduce the various algorithms. And one thing that I want to say is that, throughout the whole talk, I'm going to give all these algorithms and, performance analysis. But one thing that I think is most interesting to people in this audience is proofs of optimality. So I have minimax bounds for anything that I will say during this talk. And as you might know, coming up with minimax bounds in online learning algorithms can be a little bit more interesting than classic passive learning algorithms or supervised learning algorithms. And then I will talk about future works. This is just the first step in this direction. So I believe that there is a lot that should be done. So as you know, recommendation systems have a lot of applications. We use them all day long, every day. And right now I'm going to talk about this online collaborative filtering, in which there's a system that makes sequential recommendations to users. These recommendations are only made based on the historical data. So when the system recommends an item to a user, it looks at the feedback and makes the next recommendation based on just this feedback. So this is in contrast to something that's called collaborative, and I forgot the other name, but content filtering, I guess, but the one that the profile of the user. So for example, the gender, the age, the education, and then use that kind of information to recommend items. We don't use that. We just use the historical data to make new recommendations. And as I said, this is an online system, so it's sequential. You look at the data, you make new recommendations, and so on. So at each time t, there are n users in the system, and each user is recommended a new item. We denote that by A sub U and T. And then the preference of user U for item A sub U and T is denoted by L sub U and AUT. So we assume that this feedback and the preferences are denoted by this binary valued random variables +1 and -1. So this is just like or dislike. And the measure of performance for a system given a known time horizon is what we call regret at time t. So t is the time horizon. We designed the system to perform up to time horizon t, and it is expected number of disliked recommendations per user by the algorithm. So as the algorithm keeps...
Can I ask a clarification?
Sure.
Is there a particular reason why the item, the new item, depends not only on the time at which it is presented, but it also depends on the user?
So you make different items to different users.
I see.
Right. So you don't recommend one item to all users. So at each time you have to make a recommendation to all users, but these can be different recommendations, right? So the point is finding for each user, finding an item that they probably like and recommending that.
All right, thank you.
Right. So yeah, going back to the measure of performance, this is expected number of disliked recommendation. I just want to mention that expectation is with respect to randomness, both in the model and in the algorithm. You know, whatever the algorithm does, it might be random. And again, like regret here is used with a slight abuse of notation. Usually regret is denoted to denotes the performance of the algorithm with respect to the optimal algorithm. But here we just try to minimize, you know, the expected, we just look at this value as the regret. And as I said, the goal of the algorithm is to make as many good recommendations as possible. You can think that, you know, good recommendations means money, right? You wanna make sure that people, you know, like the items that we're recommending. So we just try to make as many good recommendations as possible. And one thing that I want to mention is that this is with respect to known time horizon. So we're designing all these algorithms, and everything I say during the talk is given a fixed known time horizon. What is the optimal algorithm? What is the performance, and so on. You might say that, okay, so you know, the whole point of, you know, designing online algorithms is that you want them to be continually performing good, you know. So why do we assume known time horizon? And the answer is that this is just the first step. There are these off-the-shelf standard tricks that basically can take any algorithm designed for known time horizon and transform it in an algorithm that works, you know, sequentially good for any time horizon. With unknown time horizon, basically. That's why, just for the sake of simplicity of the presentation, I'm going to assume that we know the time horizon. So that's not a big limitation. And the other thing I want to mention is that this is a major thing in this talk and in this system, is that we assume that each user is recommended a new item at each time. So this is, if you think about it, this is a major difference between this setup and classic multi-arm bandit problems, in which in classic multi-arm bandit problems, the goal is to find the best optimal arm, and then after you find it, you can just keep on pulling the optimal arm. You don't need to do any more exploration. But here, we're assuming that we are never done exploring, basically, because we have to keep on recommending new items to users. And again, in the context of recommendation systems, it makes sense. Like, if you recommend a song to a user and they like it, I mean, they like it, they enjoy it, but they don't want to keep on getting the same recommendation over and over and over again. And this is like, as I said, in the practical sense, it makes sense, but in terms of theory and algorithm design, this changes things, and it makes a big difference from this setup and the multi-arm bandit problems. So this is just the algorithm, the system requirement, and the measure of performance. If you have any questions, please interrupt. So classic recommendation systems are based on two frameworks, basically. One of them is called user-user framework, in which the goal of the recommendation system is finding similar users, and similar users are the ones that basically have similar taste in items. So first you try to find similar users, and then if you say that, for example, these two users are similar to each other, and then one of them likes some item, then I guess that the other one likes this item as well. So that's how I'm gonna make good recommendations. Alternatively, there are item-item algorithms that tries to find a similarity between the items and looks at the structure in the item space, and says that if these two items are similar to each other and a user likes one of them, then probably this user is going to like the other one as well. So that's how I'm going to make good recommendations and use the historical data. Alternatively, this whole recommendation systems design usually are formulated as a matrix completion problem, in which you have a matrix of preference of users for items, and then you try to some subset of entries of this matrix corresponding to the recommendations you've made so far, and you try to learn the remaining elements of this matrix. Obviously, if this matrix is arbitrary, there is nothing that you can say, you can't learn anything. So usually there are these assumptions that this matrix has certain properties. For example, you can assume that it's low rank. That's the most common assumption. And as I said, the goal of this formulation is usually learning all the elements of this matrix accurately, which is one difference between like our setup and what we have here, because in our setup, we don't try to learn the preference of all users for all items. We just care about making good recommendations. And as we see in a lot of cases, actually, learning preference of users for all items is actually not the right thing to do. It's wasteful. It's better to, just ignore part of this preference matrix. Online learning in the context of recommendation systems has been studied before. And then, the basic idea is similar to all the other online learning algorithms, that there should be a balance between exploration and exploitation. In exploration, you try to find similarity between the users and items, and then the preference of items and users for items. And in exploitation, you try to make recommendations that are good. Based on historical data, you got some information about the model, and then you have some reliable, recommendations, and that's how you make money, basically. So this work is in continuation of two papers that have been done in MIT by Guy Bressler, my advisor, and Deva Bhattacharya, and George Chen and Louis Wolof before. We basically completed the picture. They started this idea of online collaborative filtering and theoretical analysis of that, and we just tried to make a coherent picture out of that. So I said everything I wanted to say about the system requirement and the measure of performance. Now I have to tell you about the underlying model, right? We have to make some assumptions about the underlying model of preference of users for the items. So as I said, I'm going to assume that there are n users in the system, and each user likes or dislikes an item. So that is denoted by -1 and +1. So L sub U and the I is the preference of user U for item I. And so this is the picture on the left is the most general, model that we can have. The latent variable model that we assume is kind of a discrete structure. It says that there are certain user types and item types, and it assumes that users of the same type all have the same preference for all the items, and items of the same types are liked or disliked similarly by all the users. So there's this discrete structure that, basically there's the grouping between users and items, and that determines the preference model. Initially, we don't know this partitioning over users. We don't know the partitioning over items, and we don't know the preference of user types for item types. So we know nothing. We just know that, there is this grouping. So just to introduce the notation, KU denotes the number of user types. KI denotes the number of item types. And initially, we assume that a type of user U, denoted by tau sub U of U, is uniform over these KU types, and type of item I is uniform over the KI item types. So everything is just initially uniform. Regime of interest that we're looking at is this thing, which is KU and KI are both larger than log n. And remember that n is the number of users in the system. And we assume that, we don't explicitly look into asymptotic in n, but we care about how performance and things change as n grows, right? So all our results are for finite n, basically, but we care about large n, right? So And as I said, like if you think about KU and KI, the number of user types and item types, if they are smaller than log n, then the algorithms and the problem becomes a little bit trivial and non-interesting. So this is the regime that we're looking at. And then the assumption that KU is smaller than n, remember that KU is the number of user types and there are n users in the system. So if KU is larger than n, then you can make some statistical, basically games to just like assume that, oh, there's actually only smaller than n number of effective user types. So again, this is without loss of generality. And then there's this preference matrix denoted by M of size KU by KI, which is the preference of user types for item types. So preference of U for I is the element in the matrix M corresponding to tau U of U row and tau I of I column. And again, a priori, we assume that the elements of this matrix are IID distributed with on +1 or -1. So each user type likes or dislikes each item type with probability half. Generalization of this model to arbitrary probability P is kind of trivial. Generalization of this model to IID noise is also trivial. We have one version of that in the paper, in which preference of user U for item I is this preference of user type for user type of U for item type of I plus some IID noise. But more complicated models is something that should be studied, and that's part of the future. So again, is there any question about the model? Just to review again, like the whole like preference of all users for I items can be captured by this partitioning over users denoted by tau U of U and partitioning over items by tau of I and this matrix M. So you can think that the preference matrix L can be decomposed by some smaller matrices as follows. So one would think that, oh, okay, this is actually kind of similar to low rank assumption, but it's not, because the assumptions that we're making are underlying kind of combinatoric, right? This like left matrix and right matrix, they have like the left matrix has only 1, 1 at each row. The right matrix has only 1, 1 at each column. So generalization of these to like low rank matrices and so on, it is an additional non-negligible step. So yeah, that's all I'm going to say. Is there any question?
Yeah, just to make sure I fully understand. In tau U, 1 means what exactly, and what 0 mean?
Oh, this is this is just like I'm not going to use this notation again. So this matrix is basically matrices of users for user types. So here I assume that I have 3 user types, and this matrix is denoting that, for example, first user belongs to first user type, second user belongs to second user type, and so on.
No,
so preference.
But when you have a 0, for example, what does that actually mean?
Here it means that this user does not belong to that user type.
All right.
Right. So previously, so tau U of U is a function from users to user types, right? And this is a discrete function, like both the domain and the range are discrete. I can denote that by a matrix, right? That if the user type of this user is, I don't know, K, then
so implicit is the assumption that some users have nothing to say about certain types.
No, that's why I'm saying that this matrix cannot take any arbitrary form. This matrix has this property that each row has 1, 1, and all other elements are 0.
Oh, I see. All right. Fair enough.
Yeah, that's why I'm saying that, this is not general, like low rank assumption. This is very specific, because these two matrices have this property that left matrix has, in each row there's 1, 1, and all other elements are 0. And in the right one, each column has the same property.
All right, thank you.
So just to review, the system requirement was that at each time t, each user is recommended a new item. And the measure of performance was the expected number of bad recommendations per user by the time t, which was the known time horizon. And there were KU user types, KI item types, and this like denser, smaller preference matrix denoted by M. And a priori, we assume that user types are uniform, item types are uniform, and the elements of preference matrix are also IID and uniform. And again, like more important than like the bias of like IID being like probability half is the uniformity assumption that we assume, and independence. Uniformity and independence are both important.
I have a question. So far, the randomness is in the M matrix, right?
So this is the, and also the assignment of types.
Right. Now, how do you, the A process is also random, right? In your case, or is that fixed? The AUT,
AUT is what the algorithm designs, yeah.
So it gets its underlying probability structure from the algorithm and from M? How do you get
So algorithm just looks at historical data. So I can, come up with this, just the variables, which is historical data, whatever I've recommended so far and the feedback I've taken so far, from them.
It's a deterministic algorithm then. Yes. There's nothing random about it.
There is some randomness.
Okay. Right.
There is some randomness. Yeah. For example, like my algorithm says, like pick a bunch of items, right? And then these items are going to be random, right? So the types of these items are going to be random. So there is some randomness. The implemented, like when I code it, actually, it's deterministic, right? So that's all I can say.
Find out how, when you compute such an expectation in general, how do you get the underlying joint distribution that is needed to compute this expectation?
That's really needed. That's the details of the proof. Yeah, it's like a lot of times you can use linearity of expectation. In the upper bounds, usually you get, in the performance analysis, usually you get the linearity of expectation, so things are a little bit easier. But in the minimax bounds, you have to have this kind of chaining arguments, because this is expectation with respect to history. So you can't like get rid of that, right? So yeah.
In the lower bound proofs, right?
In the lower bound proofs. That's why I'm interested in the lower bound proofs. Yeah. Because regardless of realization of history, I have to say this expectation is lower bounded, right? So that's what makes it interesting. Yeah.
Thank you.
Yeah. Thanks. Very good question.
So here M is fixed. The matrix M is fixed before you start the algorithm, right?
Fixed unknown. Yeah.
Fixed and unknown. Okay.
Yeah.
And M is the matrix that you're going to learn.
And also I don't have to learn M. I just want to make good recommendations. So if it means that I'm not going to learn M, it means I'm not going to learn M.
Okay.
Yeah. Like, obviously I have to learn parts of M, but what I'm saying is that measure of performance that doesn't require like learning M completely.
I see.
So just to get so this was a recap, this is slide. Next slide is just like what we're going to see. And what we're going to see is the following, is that, as I said, we're going to introduce some optimal algorithms. And we're going to show that optimal algorithm depends heavily on the regime of parameters. So the parameters that I had was number of user types, number of item types, number of users, and time horizon. So depending on the configuration of these parameters, the optimal algorithm might do something completely drastically different from each other. And then, as I mentioned multiple times, proof of optimality is extremely important and interesting. And the other thing is related to the question that you just asked, that in a lot of regimes, actually, the optimal algorithm does not learn everything about the model. You don't need to learn, everything to make good recommendations. And in what comes next, first, I'm going to introduce a user algorithm that just uses the structure in the user space, just looks at the similarity between users to make new recommendations. and show the optimality regime of this algorithm. Next, I'm going to introduce an item-item algorithm that just focuses on the structure in the item space and ignores the user structure. And next, I'm going to introduce a hybrid algorithm that is optimal in uniformly in all the regimes, actually. So these first two parts are the paper that is already available, and the last part is under preparation.
And before you start, I mean, optimality means what exactly here?
So I'm gonna have upper bounds. So each algorithm gives upper bounds for this regret, right? It says that regret at time t is bounded by this.
But
so my lower
optimal?
bounds are gonna give lower bounds for
No,
this.
I understand, but why is this optimal?
That's what I'm saying, because upper bound and lower bounds are within a multiplicative factor of each other.
But it's not optimal in the sense that you find the minimizer or the maximizer.
No. This is optimal in the sense that in the up to multiplicative factor. Yeah.
Thank you.
Yeah. I'm sorry, you're on mute, Prakash.
You're looking at big O of n upper and lower.
No, I'm not looking at asymptotic. I look at the finite value of everything. But there is a multiplicative factor, and the multiplicative factor actually is not always constant. It's like sometimes it's log, but it's log when the actual term is polynomial. So yeah.
Why is it called optimal? I mean,
this is a little bit like CS language, that when it's constant upper bound and lower bound, you say optimal. Yeah. Because in a statistical analysis, like you can't get constants, right, in a lot of cases, right?
So the algorithm could in fact be very bad, but you manage to find a lower bound and an upper bound that match in terms of the order, right?
No, but the lower bound will not be a lower bound will not be algorithm specific, right? So I think what she's saying is that, as you said, it could be a suboptimal algorithm in a certain sense, not the best among all the algorithms in the world, but the upper bound will match the lower bound, which is algorithm free. Is that correct?
Yeah, of course. Yeah.
But is it always the case that it's algorithmic or algorithm free?
Yeah. Lower bound doesn't depend on algorithm. Lower bound just looks at the system requirement, and yeah, lower bound is among all the algorithms, what is the best value of regret you can get.
I see. Thank you.
Yeah. Oh yeah, so I just wanted to show how this regret is gonna look like. And as I said, it depends on the time horizon t. And we expect that at the beginning, there is a regime in which I get some curve with slope t/2. So remember that a priori, if I don't know anything, like each user likes each item with probability half. So if I just make random recommendations, I get regret of t/2. So this is basically naive, like, ignorant algorithm. And you can imagine that at the very beginning, when you don't have enough information about the underlying model, you can't do better than that. You can't do better than t/2. But the amount of time that is bad, basically you don't have any information, it's called cold start time. And that time matters, right? That's the time that basically you can't make any money. And that's one measure that we're going to look into. So this is how all the algorithms are going to look like. But after a while, your explorations are enough. You learn, your time horizon is large enough that you can get enough information about the model to make good to start making good recommendations. So a fraction of future recommendations are going to be good. And in that regime, exploitation is going to be bigger than 0, and this curve is going to have slope smaller than half. And then there is a regime that you transition into asymptotic slope. Asymptotic slope is where you learn enough the model that after that you're just basically in the in the stationary state. And then this transition is also important. You want it to be as small as possible. But the other thing that's important is this asymptotic slope, which is how the regret increases with t as time grows in asymptotically. And as you can see, this asymptotic slope is not 0. And why is not 0? Because I mentioned that at each time you want to recommend new items to each user. So you never end up not exploring anymore. You know, as the time horizon grows, you have to explore and look into new items. And each new item, you have to learn the preference of this user somehow. So the asymptotic slope is not 0, as opposed to, you know, multi-arm algorithms, for example, that or a lot of other online learning algorithms in which you learn everything about the model, and then after that, your performance is going to be constant, basically. So this is the kind of curve that we're gonna expect, and the variations of this curve is what we're gonna see. So if there's no question, I can start talking about the user algorithm.
Sure, go ahead, please.
So as I mentioned, user algorithm looks into the structure in the user space and ignores any structure in the item space. And you know, this community, I think, having close relationship with information theorists, it's very obvious what should be done, right? You just initially, you just recommend some random items to all users as follows, and then you'll get the feedback. And if the number of random items that you recommended is large enough, you are capable of partitioning the users based on the outcome of these recommendations, and this partitioning corresponds to the partitioning according to two types. Again, if the number of explorations you've done is large enough, and then after that, there is this stationary state, again, like asymptotic state, in which at each time you have to recommend a new item to each user. So you start by recommending a bunch of items to some users to learn the preference of user types for each item. And then from the feedback, you learn that, okay, so this user type liked this item, so I'm going to recommend this item to other users of this item type, to this user type. And then I have to repeat this process because I cannot repeat the same item, recommend the same item over and over again. So this step 3 is being recommended. And I just want to mention that the initial phase in which you're making recommendations to partition users, the number of those recommendations should be proportional to log of KU. This is log of KU is a little bit tight. It should be a little bit larger than that to make sure that with high probability partitioning over users is going to coincide with the partitioning according to their types. But
I had a question.
Go ahead.
You said that initially in the model, you said once a user accepts a recommendation, then that item is out of the picture for that user, right? It's
yes.
discarded. So when you form these user groups that show preference for different items, what is there in the model to ensure that when a new item comes into the picture, that the user to item mapping will not change? So in other words, you group
partitioning over users is constant. It doesn't change according to item.
All right. Okay. And so if new items come that don't fall into the same preference categories, then you have to reinitialize you have to reform the groups. Is that how it works?
That's okay. Yeah, that could be the algorithm. It seems to be the right thing to do, okay. But that algorithm is not better than what I said. Right, so that's the loss in a constant factor, basically, right? Even smaller than that, right? So instead of doing that, I'm just going to initially recommend enough items to say that with high probability my partitioning is correct. If it's not correct, then okay, it's a loss, but probability of that is a small, right? So you remember that I say expectation. So if with a very small probability something bad happens, I'm fine with that.
All right, thank you.
Right, yeah. But like, yeah, I mean, in practice, that's what you should do, right? You have to refine your partitioning because you don't want to say that with small probability, I'm going to do bad from now on, right? Yeah, I agree, yeah. It just like all the analysis is going to get so complicated so fast that I'm trying to simplify things as much as possible. That's why I didn't propose that algorithm, yeah. So let's look at the regret curve of this algorithm. Again, so this step 1 is the exploration in which each random items are being recommended to each users. Each random item is liked by each user with probability half. So initially, we're going to have this slope of 1/2. up until you're done with step 1, which is basically C times log KU. Again, C corresponds to the probability of error that you afford, right? So I'm not going to go through that much detail, but and then after that, a fraction of time you have to do this exploration to learn the preference of user types for each item, and the fraction of time that you do that is proportional to 1 over n over KU, right? Because each time a user type learns the preference of this user type for an item, it can use this information n over KU times, right? Because there are n over KU times, roughly speaking, in each user type. So the slope is going to be proportional to KU over 2n. This is all back of envelope calculation. Obviously, as I said, the constants are not tight, and you need to make it much more rigorous, right? All the user types do not have same number of users and so on. Like, it's this uniform distribution, so you have to do statistical analysis. But the curve is going to look like this, right? There's a cold start time proportional to C log KU, and then after that you have a slope that is proportional to KU over n. And the properties of this algorithm is the following, that there is a poor initial performance and asymptotic slope is achieved quickly. Why do I say quickly? It's just because it's logarithmic in the parameters of interest, right? It's logarithmic in KU. But the slope is large. Why do I say it's large? It's because it's linear. First of all, this is linear in T, but also like this is KU over n. So if you think that KU, for example, is polynomial in n, is n to the power of alpha, this is like polynomial in n times T.
What does it mean to be infotheoretically optimal?
That's exactly what I'm not like, I didn't write the detail of that theorem, but basically I say that if Ki is bigger than is of the order of 2 to the power of Ku, then no algorithm can get a regret curve smaller than something like this. But when I say something like this, it is within a constant factor of this. And that constant is not 10 to the power 4. That constant is like 3.
Mm-hmm. Thank you.
Yeah. So this is again like not for this algorithm. So I'm saying I define this system requirement and a model preference model. For that preference model and system requirement, no algorithm can get better than this.
But just a quick comment here. What you call the regret is not what usually is called the regret in Bandit, right?
Yeah, I mentioned that. That is a
yeah, I know. But so when you answered my question by saying that you're getting a lower bound that is essentially algorithmic agnostic, it's basically based on the requirement of the system. If I were to go back to the original definition of the regret, then you couldn't make the kinds of arguments that you're making because I'm taking a difference now.
The difference does not go to 0, because of this constant, So upper bounds and lower bounds is for the regret that I defined, not right. For the with respect to
why is this operationally meaningful to have a regret? Because the regret is essentially saying this, right? I do something, let me see how much I regret not having done the optimal, right? So why is it called the regret?
The idea is that
so here, sorry, one thing. So the difference from the bandits setting is that in the bandits there is the highest, the most, the highest mean, and we are not getting it. So it's the difference that constitutes the regret. Here it's just the number of times you making the regret is just the number of times you deny a recommendation, right? So that's the way your definition of regret goes, in contrast with the bandit. No,
Prakash, that's clear. But why call this the regret? I mean, that's essentially it's the average or the expected performance, no?
With a negative sign. So you want to minimize this one. You could have looked at the opposite, +1, and tried to maximize it, right? That would be the same in the cost function, correct?
Yeah. I agree. I mean, I mentioned that is a slight abuse of notation, and it is a little bit, I've just said it so many times that I'm comfortable with it right now. But basically, the basic idea is that this is this is not as opposed to, this is not compared to like with like minus the optimal algorithm, right? I don't think that that quantity is easily even calculatable. As I said, just because there is a statistical nature of this is much more complex than multi-arm bandit. So,
but not only that, I think that you could not make the argument that you made to me that you're getting a lower bound and an upper bound that are of the same order. That's a lot harder to achieve, right?
No, the upper bound and lower bound is for what I call regression. It's not with respect. Yeah.
Thank you.
Yeah. So the basic idea that, you know, I'm willing to defend this work is that you care about the performance depending on the parameters, right? You want to see how changing the parameters is going to change the performance, and that is what I'm getting pretty tight here. So that's where the constants do not matter. And the other thing that matters is that, like, you're going to see that in different regimes of parameters, algorithms should behave differently. So sometimes exploring user space is so expensive that it's not worth looking at it, right? And my upper bound and lower bound is characterizing that regime tightly, right? So when I have upper bound and lower bound, and both of them say that you have to ignore this part of the structure in certain regimes, then I, as an algorithm designer, feel very comfortable ignoring that. Right. Although, yeah, there's a constant factor, but I know that that constant factor is not missing the main behavior of the model.
So another question about this theorem, which says that things are optimal if this condition holds. Is it because the M matrix had uniformly distributed independent?
Yeah. I'm gonna go into the details a little bit. Yeah.
So is it that the group should be roughly of the same size? That was my question. Is that the optimal one? In other words, the mapping from the items to the users, if they are roughly equally proportional, then you get this bound. Is that what it is? Meaning of this theorem?
No, it's the other way, that a structure in item estate. So let's go to the next slide and see that. So this is the regime that basically it looks like this, right? That number of item types is 2 to the power of KU. So, you know, the point of item structure, the point of grouping over items is that each item is rated similarly by, you know, users, right? So if I know that one item is rated certain way, then I make some inference about the preference of the other item in the same group, right? But if I have all the variations of item types, you know, all the possible preferences of item types, then there's no information in the item space.
Yeah. No, but
right? So
what I meant, yeah, I see the picture. That's exactly what I had in mind.
So yeah, exactly. So the matrix M actually looks very fat, right? And all the possible column realization of columns happen here, right? Yeah. So, to go into the details of proof idea. So this is the easiest lower bound proof idea, but also it's a little bit like not exactly representative of the proof techniques that I want to get into. But the proof idea has 2 main steps. The first one is making this observation that given a matrix M, if a user has rated fewer than log KU items, then the next recommendation to this user is uncertain. I don't know the outcome of this. So basically, if I don't learn the type of users, then I cannot make any good recommendation, right? This is a statistical argument. It needs to be proved. Like looking at this matrix, it is kind of obvious, right? That if I don't know the user type, for example, if I'm uncertain if a certain user belongs to the first user type or second user type, and I want to make a recommendation of certain item to this user, I don't know if the preference of the, like with high probability, this recommendation could be +1 or -1, right? So this is a statistical nature of this fat matrix, basically. And then the next step is showing that you need log KU recommendations to learn the preference of users over, to learn the partitioning over users. And actually, like, I mean, this might seem obvious, but when I started thinking about this project, I was thinking that, okay, so there is this grouping over users, but do I actually have to learn everything about grouping? Maybe if I just have like a posterior over the grouping for each user, then I can do some kind of posterior matching and get something out of it. And actually, this lower bound says that that's not useful. There's nothing, and you know, they very like information theoretically speaking, this is coming from the independence assumption and uniformity assumption. You know that you have to learn the partitioning over users correctly before making any good recommendations. And then the next observation is that even if you know the type of user U, if an item has not been recommended to any user of the user type tau U of U, then recommending this item to this user type is an uncertain, right? Which is again obvious. There's no structure in the item space. So you have to recommend each item to at least one user in each partition to know the preference of this partition for this item type. And putting these two observations next to each other, you get the two parts of the regret curve. And part of the second step is like this important component of lower bounds that each item cannot be recommended to more than once to each user. So that's going to appear in the proof as well. I'm not going to get into much details of this proof because honestly, like it's not the most interesting lower bound. But basically, these two simple intuitive observations that can be, formalized, give the two parts of the lower bound and, the two curves. And actually, like what you get is not like exactly this. You get regret is upper bounded by max of these two, right? And then I say that, oh, actually, max of these is proportional to average of these, right? So that's another like constant factor that I'm missing here and there, right? Like different observations give like different lower bounds, and then you know that regret is lower bounded by all of them, so it's lower bounded by max of them, and so on. So at a very high level, the lower bound, this like algorithm independent lower bound, has two main steps. I'm going to get back to this slide over and over again. In the first step, we define a notion of bad recommendations. What are bad recommendations? Bad recommendations are the ones that, given historical data up until t-1, the probability of this recommendation being successful is close to half, right? And depending on a model and so on, and it's, again, some kind of a statistical properties, I have to characterize these bad recommendations. Recommendations that have certain properties are bad. For example, in the previous slide, I showed that if a user has not been recommended anything, larger than log KU times, then any recommendation to this user is bad, right? So that's one characterization of bad recommendation. And then good recommendations are anything that's not bad, And then very obvious observation is that regret at time t is lower bounded by 1/2 total number of bad recommendations divided by n, actually. And the reason is that, as I said, like regret is expectation of total number of bad recommendations. So this is again, this is the chaining thing that I mentioned before, that you have to look at historical data here. You cannot use linearity of expectation. That's why I define bad recommendations given historical data, right? So historical data is important in definition of bad recommendation. But if I can get a good characterization of bad recommendations, and if I can get a lower bound on the number of bad recommendations, then I can get a lower bound for regret, right? Because regret is, as I said, lower bounded by the 1/2 total number of bad recommendations. And in the step 2 of the algorithm is basically like I have to find a lower bound for the number of bad recommendations. So one thing that is important is that, I have to get a full characterization of all the bad recommendations, right? If I say that, okay, this recommendation is bad, but there are certain other things that are bad, but exploration recommendations are kind of bad recommendations, then my lower bound is not going to be tight. But after I characterize the bad recommendations, I have to get a lower bound for that. And that's basically has two main kind of arguments. One is that I will show that the number of good recommendations is upper bounded by a function of bad recommendations and parameters of the model. Intuitively speaking, this means that each exploration can give you only so many exploitation. And the inherent reason is that each item can be recommended at most once to each user, right? So that's the main argument of like how I get the first type of inequality. And the second inequality is very simple. This is that the total number of recommendations is n times t, because I have to recommend one item to each user at each time. So putting all of these type of like inequalities next to each other, I get like a lower bound for the number of bad recommendations, and that gives me a lower bound in terms of regret. Going back to the proof that I just described, now what is the characterization of bad recommendations here? I say that if a user has been rated fewer than log KU times items, so this is going to be like if a user has been recommended fewer than log KU items, then the next recommendation to this user is going to be a bad recommendation, right? So that's one characterization of bad recommendation. And next one, I'm saying that if an item I has not been recommended to any user with type tau u of u, then recommending I to u is a bad recommendation. That's another characterization of bad recommendation. And then like there's some step that I'm missing here, but basically I say that, okay, but I have to have enough good recommendations, and each exploration can give me at most so many exploitations or good recommendations. So I get both of these parts. This was a very high level, just intuitive explanation of the lower bound. We're going to get into much more detail in the next step. I'm going to go to item algorithm, but if there's any question, please let me know.
Oh, it's fine. Thank you.
So the item algorithm focuses on the structure in the item space and ignores any structure in the user space. And the algorithm goes as follows. So there's this parameter that I call L. I'm going to talk about it a little bit more. At step 1, L random items are recommended to all users. The role of this step is basically learning L columns of preference matrix. So when I recommend one item types to all the users, I'm learning it corresponds to learning one column of preference matrix, roughly speaking. That's the goal of this step. So here, let's say L is 2. So I recommend these 2 items to all users. And then at the next step, I'm gonna get M items. M is another parameter that I'm going to determine later, and these M random items, and I'm going to recommend it to log KI random users. So these are the M items that I'm picking, and I'm just recommending it to log KI random users. And based on the outcome of step 2, I can cluster these M items into some partitions. And I know the preference of all users for all these partitions because I recommended L items to all users. So next step, I know the preference of all users for all of these partitions. So I can make exploitations. I can make, I know which users like which item clusters. So basically, the idea is that I want to partition item space. But I'm not going to partition all the items in the item space. I'm just going to partition items that correspond to these L item types that I learned the preference of. So I'm not going to learn the preference of all users for all item types. I'm just going to learn the preference of all users for a subset of item types, which is this L item types. In step 2, I'm just partitioning items into these clusters and similarly use the structure in the item space to make recommendations. Is the algorithm clear? Mm-hmm. So next step, these parameters L and M need to be determined, right? These are the parameters of the algorithm, and they depend on the parameters of the model. So number of item types, number of users, and time horizon. Let's look at the regret for this algorithm first. Roughly speaking, regret is this term. So at step 1, I have L explorations. I'm recommending L items to all users. So each of them are liked or disliked with probability half. So there's a term linear in L. It's actually L over 2. Next, at step 2, I'm recommending these M items to log KI random users. So each of them, these are all random. I'm not using historical data to choose these items. So each of them is liked or disliked with probability half. So that gives a term of M times log KI over N. I'm dividing by N because, again, like regret was the expected number of bad recommendations per users, right? So the total recommendations that I'm making is m times log ki, and I'm dividing by n. And then there is a probability with probability 2 minus L for a given user. Let's look at a given user. With probability 2 minus L, this user doesn't like any of the item types that I learned. So if that happens, this user actually doesn't like anything that I explored, and I cannot make any good recommendations to that. So that gives me that term of 2 to the power of minus L times T. So with the choice of M and L, this is going to be my regret. Now let's look at how I pick M and L. My requirement is that I need to have enough items to recommend, right? So how do I find items to recommend? I had this bag of M random items. A fraction of L over Ki of this bag of items were among the item types that I learned. And I want this to be proportional to T because I need T recommendations by the end of time T, right? So I need to make sure that there is this property that M times L over Ki is proportional to T. Again, I'm missing constants here, right? So I just plug in that value of M. So I'm just going to assume that M is T times Ki over L. So this is going to be my regret as a function of L. And you see that there's a linear term in L. There is a term inversely linear in L, and there is an exponential term in L. So I can pick L as a designer of the algorithm. And that L is going to depend on time horizon, Ki, and N. So depending on what is my time horizon, I will choose different values of LS star. And then depending on LS star, I'm going to pick MS star. And that's how the algorithm is going to perform. And then the performance of the regret of the algorithm, I just plug in this optimal value of LS star for that. So this is how the regret curve is going to look like. Initially, I'm going to have the cold start time proportional to Ki over N. And then there is a logarithmic part proportional to log T. And then there is another another regime in which regret is proportional to square root T. And then there is the asymptotic regime in which the slope is log Ki over N. So this is how the different regimes of the item algorithm is going to perform. And there are certain observations. The cold start time is going to be asymptotically small. This is Ki over N, so it's polynomial in N, so that's considered a small. But the transition into asymptotic slope is quite late. It's proportional to N times Ki over log Ki. But also, like, the good thing, the positive thing is that asymptotic slope is quite small. It's log Ki over N. So these are like certain, if you compare it with the user algorithm, for example, cold start time is happening earlier, asymptotic slope is smaller, but asymptotic slope is achieved later on. And then there is another optimality theorem, which says that this algorithm is optimal when basically the preference matrix is tall, when the number of user types is 2 to the power of Ki or equal to N, one of them, whatever is smaller. Again, optimality in the sense that we discussed. Is there any question about the algorithm? Okay, so I'm going to get into a little bit more details of this lower bound. This is the only lower bound I'm going to get into the details of. As I mentioned, in this regime where Ku is 2 to the power of Ki or N, my preference matrix is going to be very tall, and all the realizations of the rows can appear in this matrix, right? If I have Ki columns and Ku equal to 2 to the power of Ki columns, then all the realization with high probability appear. And now I have to characterize the bad recommendations, right? And I'm going to make two observations. One is that, again, if an item has been rated by fewer than log Ki users, the next recommendation of this item is uncertain. So basically, if I don't know the item type of certain item, recommending this item is not a good recommendation. And learning the type of an item requires log KI recommendations, exploration recommendations. And the next observation is that even if I know the type of item I, if I've never recommended it to a certain user, and if I've never recommended any item of this type to any user, to a given user, that I don't know the preference of this user for this item type. So that's also a bad recommendation. These are, again, like very simple ideas, but the exact characterization of the first part requires something like a phenotype argument. And the second part is just basically like very simple, like looking at the preference model. So going back at the structure of the main structure of the proof, we have the characterization of bad recommendations, and now I have to, find bounds for the number of bad recommendations. And as I said, bad recommendations happen if U has not rated any item with. So recommending I to U at time t is a bad recommendation if U has not rated any item with type tau I of I up until time t. This is according to the model. And then item I has been rated by fewer than log ki users. This is the phenotype argument and so on. This is what we discussed so far. So now that I characterize the bad recommendations, I have to find bounds over them. This is the systematic part of the lower bound. This is what kind of distinguishes this from like more, a lot of work that's done in the lower bound, minimax upper bound, lower bounds of the online learning algorithms. That to get constraints on the number of bad recommendations. So remember that I want to find lower bounds on the number of bad recommendations for any algorithm, regardless of any historical data they've taken so far. To do that, I'm going to introduce this notation. F sub t and G sub t is just depends on time horizon. This is just the number of items. So ft plus sub gt is the total number of items seen by the algorithm up until time t. I don't know what is this number. It could be large or small depending on the algorithm and depending on the historical data, right? But this is just this number, ft. This is what I'm defining. And to be precise, f sub t is the number of items rated by more than log ki users by the time t. And G sub t is number of items rated by fewer than log ki users, but more than one user by time t, right? So going back to the notion of bad recommendations, I know that F sub t denotes the items that can be exploited, right? Because I've recommended them enough to users. So potentially they can be exploited in the best case scenario. G sub t are the items that I've touched, but I haven't explored enough to be able to recommend, right? So these are the lower bounds on the number of bad recommendations that I get. These are just 3 lower bounds depending on F sub t and G sub t. Again, I don't know what is the value of F sub t and G sub t, but basically next I'm going to justify why these lower bounds exist. And then I say that for any value of F sub t and G sub t, number of bad recommendations is going to be lower bounded. Basically, I'm going to maximize this lower bound for any value of F sub t and G sub t. So I say that no algorithm can get better bounds for the number of bad recommendations. So let's look at these bounds and say why they exist. So first one is upper bounding number of good recommendations. And it says that this is bounded above by F sub t times n minus log ki. And the reason is that, as I said, F sub t denotes the items that can be exploited by the algorithm. But the first log ki times that these items are touched, they are not good recommendations, because if an item has not been rated more than log ki times, then it's not a good recommendation. So these items can be recommended in a good way only n minus log ki times, and not more than that, because each item can be recommended to each user at most once. So this is how I get that first inequality, which is basically, as I said, it's a second characterization of number of bad recommendations and the fact that each item can be recommended at most once. The next one is, again, looking at the second characterization of number of bad recommendations. And it says that these items in F sub t have been recommended at least log ki times. And the first log ki times that they were recommended, they were bad recommendations. So it is lower bounded by F sub t times log ki. And the last inequality is a little bit more interesting. It is looking at the fact that each user needs t recommendations by the end of time t. Let's see how that depends on F and G. So remember that F plus G is the total number of items touched by the algorithm. And these are the items that I'm just like drawing randomly, right? A priori, I don't know anything about the type of items. So roughly speaking, F plus G divided by Ki is the number of items I have in each item type in all these algorithms. So each user requires T recommendations. So T times Ki divided by F plus G is the total number of item types touched by each user by the end of time T, right? And remember that according to the first characterization of bad recommendations, if a user U has not rated any item of a certain type before, the first time an item type is recommended to a user U, it's a bad recommendation. So basically, and then there are n users in the system, and that gives me the the lower bound of like Ki divided by F plus G times Tn. So I have these three bounds for the number of T lower bounds for the number of bad recommendations. And again, I said that this number F plus G depends on the performance of the algorithm, realization of history, and so on. But the point is that for any realization of F and G, the number of bad recommendations is going to be lower bounded by these two terms. So the regret is going to be lower bounded by the max of them. And that's what's going to give me these two terms. Oh, sorry. That's what's going to give me the two parts of the regret curve. So that's going to give me this the quadratic part, the square root of t part at the linear part. This part that's log t is a little bit touchy. That's I'm not getting that in the lower bound, but that's the gap that I get that in the logarithmic sense, basically. So the gap between upper bound and lower bound is up to logarithmic factors in addition to constant in this regime. But that's a small regime, and it's yeah. But that's the main philosophy of the lower bound. Is there any question?
Yes, I have a question. So please indulge me because I'm not familiar with
this. Sure.
And you see, you mentioned this phenotype bound. So I've seen some of the literature, and the idea is that when you do converses, things depend on the history, and somehow it should be good for any history. And one way of getting around the problem is to condition on something so that you have some kind of conditional independence. And then you use a variety of information theoretic bounds to get some expressions which you optimize. Now, how do you technically surmount the problem that is posed by the history here? I can't.
Yeah. The phenotype actually has nothing to do with history. So that's exactly the beauty of this whole thing that I'm interested in. I'm not looking at any realization of history. I have a certain summary of history, and I say that given this realization of summary of history, certain things are bad recommendations, right? And then these, that summary of history is basically like characterization of bad recommendations, right? That's the phenotype, right? That phenotype is saying that given certain events happening in the history, the next recommendation is going to be bad. Right, I'm going to talk about that in a little bit. And then in the next step, I say that, this characterization of history entails that the number of bad recommendations should be lower bound, not certain things. Right, and then in this case, summary of history is basically this parameter F sub t and G sub t.
Therefore,
right.
These things, are they combinatorial in nature, the bounds, or are they probabilistic? That's the other thing.
So the first part is the step one is a statistic, probabilistic. The second part is purely combinatoric.
I see. Okay.
That's how I separate these two, and like keep track of it. Otherwise, it's as you can imagine, it's very hard to say for any realization of history about how. So basically, in the first part, I'm not going to look into any realization of history. I say that if the history satisfies certain properties, then this thing holds. Probability of next recommendation given this realization of history is close to half, right? So that's the characterization of bad recommendation that I keep on saying it's interesting, and that requires a little bit of phenotype argument, right? Here, for example, it's like when I say phenotype, it's exactly this. If an item I has been rated by fewer than log ki users, that's a summary of history, right? I say that whatever happened in the history, I know that if an item I has been rated by fewer than log ki users, looking at the history, I can deterministically verify if this statement is correct here or not, right? So this is a function of this deterministic function of history. So that if this event happened according to the history, then this recommendation is a bad recommendation.
So you don't have the luxury of conditioning on aspects of the history and then getting some kind of conditional independence which can be exploited in the analysis. You don't have that. I mean, that arises in bandit problems, but here you don't have.
A little bit of that is happening, but not too much, because that's too hard to keep track of, like all the possible recommendations and all the possible feedback. That's a little bit of like largest data space to keep track of, right? So basically, that's why I keep on saying summary of history.
Okay.
Yeah, I mean, that's what makes this, in my opinion, a little bit more interesting, because when you think about like designing complex systems, you can't look at any realization of history, right? But you have to look at like certain aspects of history and say, this is the aspect that matters to me. But in bandit, for example, the upper bound or lower bounds, or the numbers, or like, you don't think about like distribution of all the realization of like, the pools that you had or the outcome of those pools, right? You look at the summary of that version.
So you cannot, for instance, it's not clear how one could perhaps say these are historical events that are typical in some sense, not the typicality that's used in proofs in information theory, but there are various types of historical events, and they can all be bunched together to constitute a summary, and then it suffices to examine the behavior condition on this kind of history that lies in certain type classes. Again, types being loosely defined, I don't know what it would be.
Yeah, I understand what you're saying. Yeah. Not exactly, because I'm designing an algorithm, right? So I can, like, if I say that for certain events that happen, my algorithm performs bad, then you say, okay, let's change the algorithm such that these events don't happen, right? So
in the converse, you can't do that. In the converse.
Yeah, but I want to say for any algorithm, right? So
okay, right, okay.
Yeah. I just want to mention that I think I understood what you meant by that conditional independence argument. You meant something like sufficient statistics of history, right? Like, I'm not looking into sufficient statistics of history. I'm summarizing it in the sense that I'm losing a lot of information, right? But the point is that that's enough. Still, I get tight bounds using that. So this is like important aspects of history, basically, like in this specific regime. So the idea is that since this matrix is so tall, these are the only bad recommendations that the optimal algorithm would make, right? Like optimal algorithm, that's why you have to like really think about the model setup and the algorithm to figure out the complete characterization of bad recommendations. And then I mean, next I'm going to talk about the hybrid algorithm, and everything is going to become much more interesting, although I don't have all the details of that proof. But I'm actually not going to go through the details of the hybrid. Is it okay if we move on to the hybrid algorithm?
Yeah, of course.
Yeah. So a hybrid algorithm. So as I said, like these were a little bit like corner cases, right? Either the number of user types were too large, or the number of item types were too large, and then they were optimal in those regimes. But what about like non-corner cases? And in those cases, ignore this thing. Sorry, this is ignore that thing. So in the hybrid algorithm, which is an algorithm that is universally optimal in all regimes, is actually quite simple. So initially, when the time horizon is small, you do actually item. And then after a while, for a little bit larger time horizon, when it's worth it, you do user. So you start actually ignoring a structure in the item space. And then after a while, again, it becomes useful again, it becomes beneficial or optimal again to look into item space. But you don't do pure item. You do a joint version of item that I will describe in a minute to explore the item space. And then at the asymptotic regime, you just do the pure item. There's nothing more to say. And the only thing that I need to describe is this step 3, which is the joint version. Remember that in item, you learned the preference of all users for these L item types. And to do that, you recommended these L item types to all users. Here, since by this time, you know the partitioning over users, you don't need to recommend those L item types to all users. You just need to recommend them to one user per partition. So that gives the regret bound, which is proportional to this. So to learn L item types, you just recommend these L item types to KU representative users from each partition. And then you optimize over L again. And after you do that, you get an LS star, which gives this term in regret. So this is going to be the performance of the algorithm. And I want to emphasize that this is, sorry, I just want to mention something about this result. This is kind of in a very specific regime. This curve is not what you always get. The optimal algorithm, depending on the characterization of these parameters, might skip any of these regimes, right? So you might end up not starting with item. When the cold start of user is smaller than cold start of item, you actually start by doing user and ignore the initial item. And then you might end up ignoring the user part. You might just do item and joint and then asymptotic. Or you might even ignore user and joint. This is going to become like the classic item that we had, that you start with item and then you get asymptotic. So I didn't go through the details of all that regimes, but depending on the configuration of the parameters, you might skip any of these 4 regimes that I described. And again, like in my optimality results, all of these transitions are tight, actually. Like I get exact tight transition when you get rid of like this regime and how the regret curve is going to be. What was your question?
No, I lost track of it.
Sorry.
No, that's all right. Yeah. No, it had to, it had to do with the square root of t. Where does that come from? Why this particular? Is there some concentration result that is underlying all this, and not all of this? Some underlying something that brings about.
It comes from these 2 terms, right? That one of them is linear in L, the other one is inverse in L. So when you optimize them, you get the square root.
Okay.
Yeah. So whenever you look at the item structure, you have something like that. The linear term is price of learning the preference matrix, and the inverse part is price of partitioning, right? Basically. So you need to do both of them, and that's how you get the square root t. And actually, like these regimes that I told you, that you get rid of like user and you just do item joint and so on. This depends on the price of exploration, right? As I said, you have a price of exploration for learning preference of item types. You have a price of exploration for learning preference of user types. You have a price of exploration of partitioning over item space or partitioning over user space. So whatever has a smaller price, that's what you do. And in certain regime, like for example, number of user types can be so large that it's never worth exploring user space or partitioning users. So that's when you just get rid of user or so on. Yeah, and again, like in terms of like algorithm design, this is very interesting that this is actually the practical part of the work, right? That it's telling you that actually, like when I tell you the model, model has all this structure, it seems unobvious that the optimal thing to do is ignoring part of a structure completely. Like I'm telling you that there's this partitioning over users that has this structure, but in certain regime, you should completely ignore this information and just assume that everything is independent of each other. So that's the interesting part. So the last thing I want to mention is this idea of the lower bound for the hybrid version. As you can imagine, that's going to be so much more complex because I'm not in these corner cases. So characterization of bad recommendations is a little bit more complex. But the basic structure is going to be the same thing I told you. I'm going to have a characterization of bad recommendations and then the lower bound on the number of them. And I'm just going to tell you what my characterization of bad recommendations is going to be. And it's actually like easiest to read through it. Let's look at the first one. So recommending I to you at time t is a bad recommendation if, for example, u has rated fewer than log k u item types, which means that I don't know the type of u, and I has been rated by fewer than log ki user types. So that means that if I don't know type of u and I don't know type of I, then recommending I to you is a bad recommendation. The next one says that if I know the type of u and I don't know the type of I, and I has not been recommended to any user of type tell u of u, then it's a bad recommendation. The vice versa holds when I know the type of I, but I don't know the type of u. And then the last one is if I know the type of I and I know type of u, but nothing from type I has been recommended to anybody from type u, then still it's a bad recommendation. These are, again, like phenotype arguments that you have to prove, right? You have to say that you need this information. Otherwise, the probability of recommending you, like you liking I is close to half. And the next step is going to be the very complex part that I need to like summarize history in terms of these number of bad recommendations and come up with the lower bounds. I'm not going to go through the details. I'm just going to tell you what would be the summary of the history. And again, I'm going to have this F sub t and G sub t, which is the number of items the algorithm has touched by time t. But there is this other variable, which is W sub t, which is number of user types who have rated more than log KU item types. So basically users that have the potential of being partitioned, right? And again, I'm looking at any algorithm. I'm not committing to a specific algorithm. So my algorithm, for example, could partition some of our users and then partition some of items and then, just do something mixed up, right? So WT could be something smaller than 1, right? And I have to say that for anything that the algorithm has done, I have to characterize this like some relationship over these parameters according to the characterization of bad recommendations and get the lower bound. Yeah, I don't go through the details of that. That's just too complex. But the interesting thing is that we can actually get this relationship based on these characterizations and get tight lower bounds for all the regimes of that complex curve that I showed you. And just going over the conclusion, again, like it's interesting that the different parameters entail very different, drastically different algorithms, and some of them just ignore part of information that you have about the model. You have to exploit both user structure and item structure. The way I presented the talk, it seems very obvious, but in practice, a lot of papers that you see focus only on one of these algorithms. Usually they do item actually. In the asymptotic regime, the algorithm learns the model perfectly, which means that it learns the preference model, but still the regret is not going to go to 0. You have to keep on doing exploration because it's the assumption that you can only recommend one item once to each user. And then the information theoretical lower bounds. I talked about that a lot. I want to just briefly mention the future work that, as I said, the model that I introduced is admittedly rather restricted. I assumed IID elements in this M matrix, partitioning over users, partitioning over items, are not only uniform, but are independent of each other. That there is something that can be done about uniformity maybe, but independence is much more important. Like independence in matrix M is quite important. And I mean, this like discrete structure is kind of something that we need to move on. So as I said, IID noise is something that seems trivial and like not too interesting. Classic information theory techniques can take care of that. But a structured noise and non-uniform assignment of types is quite interesting. other practical problems that need to be addressed is the problem of misspecification. How can we characterize algorithms and their performance and lower bounds in the case of misspecification? And something that I'm very interested in is the low rank assumption. I relied heavily on the discrete combinatoric structure of the model. So what should be done in the low rank assumption? That's something that, yeah, future work.
Well, thank you very much.
Thank you.
Time for questions.
So I have a question. So I was wondering, so if the item space, like every partition in the item space had like a large number of items in it, wouldn't a bandit setup kind of work here? So for like, what I have in mind is, let's say a user, you identify which partition is the user finds most favorable. And then you, instead of like, because there are many items in that particular item partition, you can just keep recommending like one after the other on that from that particular partition.
Yeah, I think what you're missing here is that, you know, to assume that there are many items in each partition, you need to explore a lot of items. You need to touch a lot of items and recommend each of them to a bunch of users to learn the preference, to be able to partition them. Right? When you touch a new item, you don't know which partition they belong to. You do have to do some exploration to do that.
I see. So,
right. So that induces some cost. So you like the size of your the number of items in each partition should be actually as small as possible.
I see.
Like you don't want to be wasteful, right? You don't want to have too many items in each partition and not use them, not recommend them.
So like, would this idea make sense if, let's say, like this algorithm has been running and a new user joins in the, like at some point in the middle? Or
I'm sorry, I didn't understand that.
Let's say like, you know, so you have learned some recommendations and like some learning has already taken place. And then you have a new user joining about whom you know nothing, right? So like, would this algorithm be able to handle that, or like would you need to do something?
I mean, this algorithm in this version, obviously no, right? But you know, we can say something about that. For example, if the algorithm is relying on the structure in the user space, then you have to like put this user in a partition, right? So that requires some exploration. So you need to do that. But if the algorithm relies on the structure in the item space, then the only cost, you don't have to pay additional cost for partitioning the items, right? You just have to pay the cost of learning the preference of this user for each item type.
Yeah, that's what I was saying. If you have a new user, then learning the preference of this particular user would, like, you could do that using a bandit problem.
Okay. Yeah, I didn't understand the relationship to bandit. Yeah. I still don't understand the relationship to bandit actually.
So if you already have the item partition there and you have a new user coming into this setup, then to learn the preference of this new user, you could use a bandit problem. That was what I was going for.
Yeah, I think I understand what you're saying. It's just that, you know, okay. I think I understand what you're saying. It's just that it's a little bit simpler than bandit problem in this setup, right? Because you have some partitioning over items. So like what you would do is what I would do is the following. You look at the first partition, like if I want to focus on this new coming user, you look at the first partition. I recommend one item from this partition to this user. If they like it, I'm going to recommend everything else in this partition to this user. And then after I'm done, I'm going to move on to the next partition. If they like it, I do the same. If they don't like it, I move on to the next partition and so on. Yeah, there is this sequential version. And going back to what Prakash said about the user algorithm, there was a dynamic version of user algorithm that you mentioned. And I told you that, yeah, intuitively it should do better, but it's only a constant factor. There's a dynamic version of item algorithm that does that, right? That I said that with probability 2 to the power of minus L, you don't like any of the part. So the problem is that I'm using the same number of item types for all users, right? That doesn't seem obviously true, right? It makes sense that, you know, you start with a small number of item types, and then that's going to be enough for some users. So you only focus on like additional item types for remaining users and so on, right? You can imagine like having this geometric group of number of item types and so on. That doesn't save more than log t, actually. So that's why I didn't include that. That's like much harder to analyze, but just like, so I was maybe log t, not even that. So yeah, I think that's even similar to what Sagnik was mentioning.
I see.
I have a quick question. If I understood correctly what you were doing, is it the case that the item types are driving the user recommendations?
When I'm doing the item or the joint version, yeah.
But let's take an example which I have lived, because when my nephews were very young, they like this sequel or this sequence of movies called The Police Academy. And so I can easily imagine that the first one might have been something that I may have looked at or I might have viewed. But when it was Police Academy number 9, I'm not so sure I would have recommended it. So how does that play in the system that you have here? In other words, what I'm saying is that I personally find it strange that only the category in which the item falls really determines the recommendation, because what you're saying, either I'm an action movie type of guy or I'm a romance movie type of guy, but nothing else. Well, What about my desire to discriminate between action type movies, right?
That's a very good question. Okay, this is something very exciting I want to talk about. So let's look at this paper. So there's this paper. Okay, so that goes back to the notion of like this grouping over items, right? That seems too simplistic, as you're mentioning, that, oh, this is fixed and rigid and everybody's committing to this partitioning, right? Like, you know, your partitioning might be different from mine, right? So there is, in this work, in the first paper here, by Bressler, no, sorry, second one, Bressler, Shah, Wolof, right? They look at an online item algorithm. The algorithm is a little bit simpler than mine, and like it doesn't have optimality result, most importantly. But the model that they're using is interesting. They're modeling the item space as a metric space with low doubling dimension, right? So low, what does it mean? It means that if you fix an epsilon, I can come up with a partitioning over item space such that each partition is of radius epsilon, and then the number of partitions depends on 1 over epsilon to the power of d, right, for any epsilon. So that d would be doubling dimensionality of my space, right? So you can imagine that now I have this additional knob I can control, right? I can go for finer resolution of partitioning. I can have smaller partitions so that everybody in the partition are closer to each other, but I will have more partitions, right? So this is like a trade-off between accuracy of each partition and the number of partitions. Okay, what I have is very discrete, right? I have fixed number of item types, and each item type, like everybody falls the same place, right? So one generalization of this model is this kind of like knob of like some kind of trade-off between accuracy, like the diameter of each partition and the number of partitions. So the other one is related to what you're saying. This is separate, right? This is the other one is related to what you're saying, which is something I've been thinking about, which is like some kind of hierarchical partitioning, right? That there is this like high level partitioning over items that everybody agrees on, but then there is this low level partitioning, and then we can commit to one of these lower level partitioning depending on our preference. Like basically this picture that I have is the right picture. It's very simplistic. There could be hierarchical levels of this picture. And yeah, that's something that some people are looking into in the literature, and that's also very interesting.
What you're saying is that I can take an item category, I can subpartition it in such a way that the subpartition represent maybe a different level of commitment of my choice for that particular category. Is that what you're saying? That
That's
Police
a little
Academy
bit
9 will be really in a very tiny bucket at the end, while Police Academy 1 would have been in the first bucket, for example.
Yeah, or it could be like you care about, I don't know, Police Academy is animation. So it's like you care about animations and seasons. I care about animations and, I don't know, violence, for example, right? So the notions of character categorization that we have are different. But if you know the animation, violence, and season, then it characterizes both partitioning according to you and me.
Mm-hmm.
So that's what I call hierarchical version, right? That you don't have Cartesian product of, you can't, like the dimensionality of a space is not all possible partitioning that I can imagine and all possible partitioning that you can imagine. There's certain aspect of partitioning that we're sharing. So how can we explore that?
One quick question, and then I will go. There are many systems where instead of saying I like, I don't like, you give a gradation, like the tomato system, right? The rotten tomato system. How is this taken into account in a system or in a model like yours?
So again, like in some papers, they just do thresholding. They say that, okay, above 5 or below 5. There are other ways, but I mean, you remember the what was that competition that I forgot the name.
The Netflix competition.
Netflix competition. Yeah, people who won that competition, actually, they took into account the fact that, for example, like some people generally give higher rating than some other people, right? Like, or some people generally do this kind of like biases in. So when you look at like more than 2 value system rating, you have to take into account, like there's a lot more that you can look into, and it becomes a little bit like very application based and system. Like it gets away a little bit from this kind of like theoretical result. But yeah.
Thank you.
Sure.
You. I had a question. What Amo asked and what you responded, the way your response in the setting a priori, can you group the items with multiple coordinates? In other words, the first coordinate is the coarsest, and then the second one is a subcategory, and so on. So initially, there is the hierarchical idea that you mentioned. Namely, initially, it's the first index that determines preference, and then second, after some time, you change it to first and second, and so on and so forth. So the algorithm itself moves along. So it first looks at a coarse partitioning and then a refinement of it, and so on and so forth.
That's related to the dominant dimension that I mentioned. That's something I forgot. That as time horizon goes, probably you afford to like have a higher resolution. Yeah. Sorry, I interrupted. Is it what you were asking? That's yeah. There are different ways, but there is this, like as I said, right now the knob that I have is like kind of globally, right? And I say that this part of item space is I'm gonna look at, and I'm gonna ignore everything else. The other knob that we can have is locally, that I'm gonna change the resolution of like partitioning over the item space, and then
Sure.
So basically, yeah. This is not captured by my model, but yeah, it's doable.
In rate distortion theory, there is this notion of successive refinement by partitioning. So you're right. So in other words, first you get a few bits. So you can get if I have a poor display unit, then I see the coarse version of the picture or something that's adequate. But then if I have a high definition version, I add some bits to what we had before. And so the initial processing is done in such a way that it's done hierarchically. And then based on the capabilities of the receiver, you feed more bits. So, but the structuring is done at the outset. And then the algorithm gives more depending on demand.
Yeah. I mean, maybe here it can be the same. I mean, there are 2 ways you can look at it. One is like how many explorations so there are two main explorations. One is like how many exploration, like this log ki basically depends on the partitioning, right? So what I'm trying to say is that transmitter has some controllers also, right? That in this case, because you can choose how many bits you're revealing. And then the receiver, like both of them are algorithm in this case, but the receiver can look into like finer partitioning or larger partitions. Yeah.
Well, thank you very much. Any other questions? So, Mina, thank you for a most interesting talk. We enjoyed it. And it's a good way to close this semester with a nice talk. Thank you. And we wish you all the best in UC Davis for success.
Thank you. Looking forward to meeting after, this craziness.
Yes, yes.
Thank you.
Thank you very much and all the best.
Bye. Thank you.
Bye. Bye.
Nice meeting you. Bye.
Nice meeting you.